Yeah, so I had a very vague title, so I updated it very slightly, 2 extra words. So I'm copying Phil's tactic here of starting off with a movie to hypnotize you into thinking we've done something realistic. So the whole aim of this talk really is to try to condense into 20 minutes the work of a large team of people for the last 3 years. That's given us a lot of grey hair, but I think we've now got something quite interesting to say. Our aims are quite similar to those the work Phil just described. However, the methodology is quite different, and I think that Joop's initial point in the questions to Phil sort of really highlights why we've chosen to go down a different path. I really like this image from the Herschel and Spitzer composite of the Large Magellanic Cloud, and I think this really emphasizes the problem very nicely. You can see here, this is the most active star-forming region in the local group, 30 Doradus. If I zoom right in on this, you can see many of these exciting physical processes at play that Phil includes in his simulations. Well, actually, there's no supernova here, right? None have gone off yet, but there's a lot of preconditioning of the ISM going on here from all of these exciting effects. But the problem is that you can see there's a huge level of detail, like very fine structure in this star-forming region, and of course, these are the regions that really determine your radiative losses. So when feedback is happening, you have to consider 2 things. Not only the energy budget of what you're injecting into the system, but also the fraction of that that is going to end up doing useful work and moving gas around to eventually arrest your star formation. So unless you can resolve this sort of structure, it's our belief that really you can't extract a great deal of predictive power out of simulations. And because we can't possibly hope to reproduce a sizable and representative volume of the local universe with the sort of 300 to 500 solar mass resolution that Phil just mentioned, then you have to start taking a different tack. Okay, so zoom out again, and I'll show you in more detail why that's a problem. This, of course, even though it's a whole galaxy, it's only 3 kiloparsecs across, and for the typical scale of simulations that we're able to do that reproduce a cosmologically relevant volume of the universe, that's the typical resolution scale of your galaxy calculation. And if you're lucky, that might be the same sort of spatial scale that you attach to your hydro calculation, so if you're doing an SPH calculation. So that really, I think, indicates that it's a hopeless task at the moment with present resources, and of course this is without even taking into account that you have to include all of this extra physics. So we want to do something simpler. So this is just the train of thought behind how we set up our philosophy. If you can't compute these radiative losses from first principles, then you can't estimate the feedback efficiencies. So the best thing you can do is to try to calibrate those efficiencies by playing about with the feedback in your simulation to try to reproduce some representative local observable. So that brings us on very quickly to the issue of convergence. So Joop mentioned, this is something that I think you really do have to worry about when you're presenting numerical simulations as a means to get ab initio predictions for what's going on. So if you're arguing that you can't estimate these losses from first principles, then this really makes you rethink what's going on with convergence. So, I mean, when we say convergence, obviously we mean you've changed the resolution of your calculation. Do you get the same answer? And clearly that's a prerequisite if you want to have any predictive power. If you change the resolution, get a different answer, which one do you believe? So this has led to a convention within the field, which I think is reasonable, to try to construct subgrid models that are insensitive to the resolution, right? And this is what we're sort of introducing a new terminology we'll call strong convergence. And there's a problem, I think, with this way of thinking, in that the strong convergence demands very strong sacrifices. Because as we just said, if there's some processes that you know you can't model with a reasonable resolution, then you've got to take them out artificially. You have to eliminate them from the calculation. And so in the typical sort of simulations that in the pre-Phil era we've all been doing, the ways you do this are either to decouple the outflows from the hydro forces, so just let particles that have been kicked in feedback events just stream out of the galaxy and reconnect somewhere in the CGM, or to disable the cooling in the outflow, so you have a set-off-Taylor type solution that's not allowed to cool for some amount of time. Now I think there are all sorts of problems, and I don't want to get into the usual debate about that because I'd like to talk about something else here, but this is something that we really wanted to avoid. And a second problem, which I think is considered slightly less frequently, is that of course many of us now believe that you need to change the properties of your feedback with some sort of quantity in the calculation. So for instance, the Oppenheimer and Darvé models, they change the wind velocity with the properties such as the velocity dispersion of the galaxies. And of course that's used because the dark matter properties are the best converged quantities within the simulation. But of course what you'd really like to do is to vary that sort of stuff with the ISM properties, because the feedback efficiency of course is related to baryon properties. And so if we're doing things related to the dark matter, really that moves us closer to semi-analytics. Not that there's anything wrong with semi-analytics, but you of course want to have a complementary methodology in trying to model galaxy formation, right? So what we're arguing in a paper, which hopefully will appear this or next week on the archives, is that without this predictive power, because we can't access these radiative losses, this sort of process is not even fully necessary. If we're going to calibrate our feedback to reproduce some sort of local observable, then all you need to do when you go to some different resolution is recalibrate. So I'm going to call that weak convergence. So this leads us on to the philosophy of the way we're going about our simulations, or working philosophy at least. So we're going to appeal to weak convergence, adopt simple natural feedback schemes. So we're not going to try to include every single process and model it individually. We're going to try to wrap things up in as few processes as possible, and then we can actually learn from the simulations whether or not that gives us some sort of shortcomings and we need to add in these things afterwards. So we're not going to have any decooling, no cooling shutoff. We're only going to scale the properties if and when we do scale them with some localized baryonic properties of the ISM, so density, metallicity, say. We're only going to have one mode of star formation feedback, sorry, I should say feedback afterwards, and one mode of AGN feedback. So no explicit quasar mode or radio mode. And then we'll calibrate these efficiencies to reproduce something like the observed galaxy stellar mass function at low redshift. So it's a philosophy that's really been pioneered by the semi-analytic community. And then we'll reject anything that's clearly unphysical. So that is the philosophy behind the Eagle simulation. So here's the bird that Frank promised you. So what are these in detail? These are cosmological hydro simulations run with advanced SPH, inspired by Phil, but with extra bells and whistles, like time step limiters and different shock detection. So come and talk to me if that sort of thing excites you. Our standard resolution is 10 to the 6 solar masses in the gas. That gives us a smoothing length of 700 proper parsecs at redshift 0, so it's better at high redshift. And really this code is represents a major overhaul of the Owls code. So besides the updated SPH, we've changed a lot of aspects of the subgrid and the feedback modules there. So I don't want to go through this whole plot. This is just here as a reference. If anyone's interested later, then go through the slides offline. I really want to draw your attention to these last 2 points. So as I said, we're going to calibrate this stellar feedback, and the diagnostic we're going to chase is the redshift 0 galaxy stellar mass function as a means to tune already.
Yeah, you just said there's no decoupling of your stochastic thermal feedback, but also you bottle up the energy, right?
Yes, that's right, yeah. So it's a stochastic, we pick a heating temperature that we know if we heat to that, then we'll not get too bad radiative losses from doing that, right?
So isn't that pretty similar philosophically then?
No, not at all.
Okay.
Well, I think we should talk about that maybe at the end.
You generate waves with in advance unknown mass volume and velocities, and in the other case you impose a certain wind, a certain mass.
Okay, yeah.
And the temperature you need to heat to is computed analytically given the numerical resolution.
Okay.
It's just comparing sound crossing time across the resolution element to cooling time.
Right. So right, that's all we're going to do to get the stellar feedback chosen, and in order to pick an AGN radiative efficiency, we're going to try to reproduce the relationship between the mass of black holes and the stellar mass of the galaxies. And as I said, we're only going to vary this with local ISM properties. So getting straight to the heart of the issue, after spending many tens of millions of CPU hours developing our code and running many different models, we hit upon a whole class of models that actually do a very good job at reproducing the redshift 0 mass function. So all of these are treating the stellar feedback in different ways. They all have the same AGN feedback in there, but the stellar feedback is done differently. So this red line here, I mean, we don't have to go through all of this completely in detail, but this just dumps in 100% of the energy you'd associate with type 2 supernovae, say, so 10 to the 49 ergs for every stellar mass that you form, and you see you get a really nice relation. So this was like the first surprise that came out for us. But you can reject this on other bases that I'll show you in a moment. We also ran a model very similar to what both Illustrious and Oppenheimer and Darvey have done, scaling this with the velocity dispersion of the local dark matter around the particle. So I said we don't want to do that, but we did it just to sort of see whether it would work, and it does. And the same thing goes by just varying the feedback efficiency with the local metallicity of the gas. So you can ascribe some physical justification for doing that I won't go into it here, we can again talk about that offline. But our reference model adds in an extra density dependence to that, and that's largely to offset numerical shortcomings, so that our resolution is not good enough to really get the feedback right in the really most dense clumps that we form in the simulations, right? But all of these produce a good match to the mass function. They're all well within the systematic errors associated with the observations, right? So these are just in 25 megaparsec boxes, so these are our test volumes. And just to make the point about how we rule out some of these models, so this seemingly really nice simple model where I just dump in the same amount of energy irrespective of any local conditions fails badly when we measure the sizes of galaxies. So this is the half-mass radius as a function of stellar mass. I'm comparing here with both gamma and SDSS measurements of this from Ivan Bolshy and Shen in the case of SDSS. And you can see here, so this green case is where we dump in 100% of the energy. We get to a certain mass scale, and these galaxies suddenly become too small. And we know that this is due to stars forming at densities in the gas that are so high that the feedback scheme fails. So this sort of comes back to the point Chris made. You have to pick some heating temperature, and you want that heating temperature to be low enough that you get good sampling, because it scales with the energy that you're dumping in, how many particles you heat. But of course, if you heat at too low a temperature, then the radiative losses kick in and you start getting this problem. So when we go back to the reference model that I'll show you in a minute, in the 100 megaparsec volume, you can see the sizes are good in the range that we're able to probe.
Can you tell us what the dotted line is? Since it seems to be off from the data.
That's
the resolution cut?
Yes, exactly. So when we get down here, we know that the numerical sampling of the simulation is not good enough to measure the sizes reasonably. And up here I plot individual galaxies because the sampling of the galaxies is not good enough for the median.
Thank you.
Okay. So don't take too much away from this. I think it's scandalous that people show pictures and expect you to believe that there's some physics there. But this is what the galaxies look like in the simulation if you run 3-band type SDSS mock images on them. So we get a full range of different morphologies, which is very nice. So I promised you a mass function. So this is 100 megaparsec volume run with this reference model. And what's very exciting about this is I think that this level of agreement with the data is unprecedented for hydrodynamic simulation. So this is the sort of precision in terms of the match that is normally associated with semi-analytic models. So just to make that point, here's a bunch of alternative models. So I'll flip between the two, as well as the blue line. So you can see that I think we're doing very well here. Another point I would make is that what's slightly depressing is that all of these alternative models are using variations of effectively the same subgrid models. So I would encourage people like Greg, add a line here. These are all variations of the Spring and Holmquist model, and we wanted to keep away from that just because it's the way you do science, you have to have alternative models. So this, just to make the point about the semi-analytic models, these are the Munich, Durham and Somerville types semi-analytic models. So you can see we're doing as well as these, I think. So to come back to this point about strong convergence, how long do I have, Frank?
You have 7 minutes.
Excellent, plenty of time. So in terms of the strong convergence, I made this point about we've designed the subgrid models to really not go chasing after this strong convergence. And so you can see if I rerun one of my calculations in the 25 co-moving megaparsec volume, at twice the resolution, so this is now a very expensive calculation, we're talking about 2 or 3 million hours here, you can see that we failed to get a converged result. So this is something that we expected, but to give you an idea of how bad or otherwise this level of strong convergence is, I can compare with the same model that was used for the illustrious simulation. So this was taken from Mark Vogelsberger's paper from last year, so this is not the illustrious simulations, it's some smaller runs done with the same code, and you can see we're only slightly worse than that level of convergence. But what's important is that if we then appeal to weak convergence, which I said was the cornerstone of our philosophy, then we have the freedom to retune very slightly the nature of the subgrid model that we put in, so making very small changes enables us to recover the same sort of result as we get in the region where both of these simulations are converged.
When you say the nature of the model, do you mean you change the parameter or do you change the recipe?
Just the parameters.
Just the parameters.
Yeah, thanks for clarifying that. So you can see that there's some bumps and wiggles here, and this is because, of course, both of these simulations, whilst the initial conditions are a different resolution, they contain the same phases. So the same objects form in both cases. So the fact that these actually match is very good. And obviously you can see we can now probe down to lower stellar masses and still get a converged result. So that's nice. So I'm going to introduce a couple of plots in a moment that feature an extra model in them. So as well as this recalibrated 25 megaparsec volume, I'm also going to show some the intermediate resolution that have a higher AGN heating temperature. So the point I really want to get across here is that it's no good just comparing with one observational diagnostic. So we've already looked at the sizes in addition to the mass function, but I also think there's a huge amount of value in comparing with gas phase observations. So in this case, I'm going to show you the LXT relation. So this is doing mock X-ray observations on the simulations using the techniques developed by Amandine Lebrun and Ian McCarthy over in Liverpool. So unfortunately, we don't have many of these big objects in only a 50 megaparsec box, so it would have been far too expensive for us to run another 100. But you can see what we've done by increasing this heating temperature, you acquire a better match to the LXT relation. So we know that basically the AGN are not doing a good enough job of ejecting gas in our reference model. So I can kick up this AGN heating temperature, get a better match with the limited number of objects that I'm able to compare with, and then rerun, replot my mass function. You can see that just with a small adjustment to when we allow the AGN to switch on, I can recover as good a match to the mass function again in this model. So this is very encouraging already. Just with an extra comparison looking at the gas phase observations, we're able to say something meaningful about the way AGN work. So this is a meeting about quenching and quiescence, something I've not said anything about yet. So finally I'll come on to that. So here is the specific star formation rates of our galaxies as a function of stellar mass. So what I've done now in this plot is to basically not say there is one equal model, but I'm showing you the 100 megaparsec scatter here. So this is the 100 megaparsec median and the scatter on that. And of course, when I get below a certain mass scale, I don't want to use that simulation to show my results anymore. It's much better to use this weakly converged, calibrated model that's at higher resolution, right? So I think you can see here they match up very nicely, as you would expect, given that we've ensured that the mass functions line up nicely. And so we're able to probe all the way down to sort of 10 to the 7 in solar masses in the stars, all the way up to just over 10 to the 11. And so we're getting a reasonable match, definitely within the systematic errors that you're seeing from gamma. So I think that's important. So this is just star-forming galaxies.
So do you have quench galaxies?
Right, good point. Coming to the chase. Right, so these are just star-forming galaxies. So you see you're matching the specific star formation rates, but of course once they get up here, they get quenched. And so here are the passive fractions. So a passive fraction in this case is defined as a galaxy with a specific star formation rate less than 10 to the minus 2 per gigayear. And so we're able to compare again here with gamma and SDSS, say. And so if you ignore all of this, because we know all of this is due to sampling problems of the code, so really I shouldn't have shown this, but once you get into the regime where you're able to sample nicely, then you can see that the passive fractions match the observations very well. So we're able to...
Why are they dashed up there? Because you just have very few objects?
Yes, yeah, exactly. So there's fewer than 10 objects per bin where these are dashed. So I think the fact that these are matching up is showing you that the HN feedback is doing precisely the effect that Phil said that they're missing from the simulations. You're able to quench, and this is just, I remind you, just a single mode of HN feedback. So there's not a distinction between the quasar mode and the radio mode. We actually get something similar to that naturally just by having variations in the accretion rate. So something that looks like a quasar mode comes out when the accretion rate is close to Eddington. When it's not, we get something closer to maintenance mode, although it's still just injected thermally.
Are all the low-mass quench galaxies, are they all subhalos?
Well, so a galaxy is the stellar content of the subhalo measured in a 30 kiloparsec aperture. Yeah.
Right, but are there any central quench galaxies below 10 to the 10-ish?
Yes, but they're numerically quenched. Well, I mean, it's just the way
Yeah,
the resolution is. I mean, if we went to a higher... The ordering of these curves is wrong. This one should be valid back down to here. Sorry, that's a mistake.
Do you have this as a function of Richard?
No, but I could make it. Okay, 1 minute. Oh. So just to reiterate the point that the illustrious crowd made, so we can't have too much point scoring, we're also able to reproduce properties of the IGM at the same time. So this, for instance, is the column density distribution of carbon-4 absorbers. So these are, I think, clearly very consistent with the available measurements. You can also see that they're not too strong a discriminator of these three models. You only get significant differences at the highest column densities. Something where we fail, let's be honest, or at least don't do so well. This is the mass metallicity relation. So again, this is the reference model up here. You can see that this relation is too flat. Whereas we go to the high resolution simulation, we get something that's consistent. So what's quite strange about this, and I don't think we've got an answer to this yet, although Joe can correct me if he disagrees, what's strange is that the strong convergence of this diagnostic is actually much better than the weak convergence. So I don't know why that is yet.
But we need stronger feedback at the higher resolution, and the stronger feedback to get the mass function right. And then the stronger feedback means you blow out more of the metals for a given galaxy.
Right.
So you decrease the metallicity.
Yeah. Okay, yeah, I'll go with that. So I think the related point to that is that what's interesting is that this is completely opposite problem to what we've seen in the lustrous. So as where they were blowing out too many metals and had to introduce a separate mass loading factor, I don't think we're blowing out enough in our standard prescription. So again, just the fact that you have two different ways of doing things, I think is telling you something instructive. So my final comment before Phil kicks me off, we started off with a plot picture like this at the start of the week from Ben. I think it's easy for simulators to try to, or at least to allow themselves to feel somewhat triumphant about getting matches to data like this. And of course this is a heavily observational crowd here, so I won't do that. I will say this is not really a success, this is just a tool that enables you to basically buy a ticket to play the game of making these sorts of comparisons, right? I think this is now the level, we know that this is the level of agreement we can get with these diagnostics like the mass function. Really now this enables us to start doing some really exciting stuff about comparing with the sorts of observations that weren't calibrated in the model, right? So you can go look at completely different things like the Tully-Fisher relationship, say, and you can start making some reasonable predictions from that and start exploring the way that the physical processes are actually taking place in the simulation. So I think this is a very exciting time for us. This is sort of the beginning of, or the end of the beginning. So just to summarize, I don't think we can predict the feedback efficiency, certainly not in cosmologically meaningful volumes from first principles. So I think a better option is to try to calibrate them. And in doing so, we can relax our convergence requirements on our subgrid models so we can sort of do things in a simpler and more natural way. So the Eagle simulation is a new flagship program by the Virgo Consortium. So as I say, there's a big team of people working on this. By calibrating to the redshift zero mass function and the BH scaling relations, we're able to get our feedback working in a way that I think is doing very well. We can now get a match with the same sort of precision that until now has been really the preserver of semi-analytic modeling. And our convergence properties are well understood. I think we can really get to grips numerically and analytically with why our convergence properties are as they are. So it should be a powerful resource. Please come and talk to us if you want to use the simulations.
Whoa. Let's go from the back forward.
So, how much can I interpret the rescaling you have as you change resolution to a numerical effect or to actually probing the physical processes of feedback?
Okay, yeah, good question. So the degree with which we need to change the parameters of the subgrid models is pretty small. And I think for the most part we can ascribe these to numerical issues. So for instance, where's a good place to look? So I think this is a good example, right? So I know here I have to change my heating temperature in order to get a better match here, so in order to kick out more material from the ICM. So we know numerically, or from doing the analytics behind whether or not the feedback should work, it's just, you arrive at an answer for that by comparing radiative cooling times and the time it takes for a sound wave to cross your smoothing cone, right? So you can easily write down an equation that will tell you whether or not at a given density, when your feedback takes place around the black hole, you should expect that feedback to be effective or not. So I think for the most part, these are numerical issues. I don't know if there's any dissension to that, but yeah, I think mostly it's numerical.
Andrea?
I have a question and comment. Usually, that's what smart people usually say. I have a question and comment. I want to say it once in my life. The comment is...
That was the comments and our question.
See, I'm not smart enough yet. Okay, comment. Aren't you successful as a SAM because you are getting as simple as a SAM? Aren't you somehow losing the power of the simulation results small scales because you're kind of ignoring all this physics because you have too simple feedback recipe?
No, in fact I would say completely the opposite. I think the fact that firstly I think we're simpler than a SAM.
Is that a danger?
Modern semi-analytic models I think are far more complex in terms of the ingredients in this. And I think that's a real boon. the fact that you can do things so simply is very exciting, I think. Because I think the problem with having a simulated model that's too complex is that you can allow yourself to draw conclusions for the wrong reasons. Right? I think there's a real risk of misinterpretation with simulated models. And the same risk applies actually in the hydro, but I think you have much reduced scope for kidding yourself. That may be controversial, but I think that's a defensible statement.
Just, I want to clarify, there's a big difference between this and both cymatic models and all these other hydro simulations that he showed. And that is in cymatic models and these other hydro simulations, you generate a wind outside the galaxy. You say, I want this mass loading, that outflow velocity, and this is how it should depend on halo mass or something. Here we don't do that. We just dump energy in the ISM where a star is formed. And that energy is calibrated to fit the mass function, but the outflow rate that comes out, which affects all these galaxy statistics, we don't know. And we don't know how it depends on the mass of the galaxy. So in that sense, it's more simple, but that because it's only one feedback process.
So you don't control the
But
non-linearity.
we don't actually control. It's actually in that sense much more predictive than the other models, in my opinion.
Christoph?
So I think you made a statement that if you have actually a subgrid recipe that is strongly converged, you cannot actually drive an outflow. And I think I disagree with this statement. If you do actually model in cosmic ray physics, okay, then I might have misunderstood. Anyway, if you model in cosmic ray physics faithfully, you can actually show that as soon as you basically allow cosmic rays to be transported relative to the gas, by means of streaming or diffusion, you can drive a powerful wind self-consistently. And that has been shown by us 2 years ago and by 3 other groups, Booth et al., Hanash et al., Salim and Brian last year. And we know that cosmic rays make up a pressure fraction that is equal to the thermal pressure fraction in the galaxy, and it's just basically modeling the physics we know is there, gives you an outflow. So I think that is something which is important.
Well, I don't think that is inconsistent with anything I said, but I mean, I think the point I was trying to get across is that if you appeal to strong convergence, then people who are doing that are introducing these numerical techniques.
No, if you model cosmic ray physics, you can actually get winds.
Well, then that must rely upon the cosmic rays must not be dependent upon things that you don't resolve in the simulation in that case. And that may be different to supernovae. But that's the only way you can do it. They have to be not dependent in any way on what you're failing to resolve in the simulation. So I don't know enough about your implementation to make a reasoned comment on that.
General point, cosmic rays are not in there.
Yes.
If that is important, that's not a
That's what
scenario
we
that's
claim.
being modeled.
That's what we
here.
claim.
Then we're missing that.
Yes.
Peter, last question.
Yeah, so I was going to ask, when you compare to the mass function, you're taking the stellar mass in the simulation and comparing it to the observed stellar mass.
Good question.
And so I'm just wondering if you thought about comparing it self-consistently with observations, that is generating luminosities and then doing a fitting.
Right, so
And
no.
especially at the mass event.
It's interesting actually because some modelers choose to try to converge on the luminosity function instead of the stellar mass function. So we've chosen not to do that because there's an extra degree of forward modeling, and I'm happy to let the observers be the ones who argue amongst themselves about the degree of error that's systematically inherent to that process. But I think you made a good point, which I'm going to jump on, about modeling self-consistently between the observations and the simulation. So since Mariangela was here, I don't know if she's still around, we chose not to, well, we didn't choose not to try to calibrate against a mass function because it appeared long after we'd started. But we could have just as well chosen to go with that. So when I've quoted stellar masses in all of these plots, I should have said these are within a spherical aperture of 30 kiloparsecs. And the reason we chose that, as this plot shows, is that that's very similar to the Petrosian radius, which has been used by the previous generation of analyses of SDSS, right? So we could have done that, but that's something we're paying heed to.
Okay, I think we should break for coffee. Let's thank all the speakers.